It's fun. Let's get started. I have basically just set up a kind of summary. It might jog your memory because you might, whatever you want to ask about. But just a quick reminder: your exam's going to have 10 multiple choice questions at 5 points each, where you just say A, B, C. I'll get you 50 points. Section 2 comes next. That gets you 250 points. Section 2, although it has 10 questions, that doesn't necessarily mean there's one question. There could be an A, B, C to it, right? That's all that means. And pretty much you got to show working for all of those, unless I clearly indicate in the question you don't need to show working, but most of the time you will. And that's going to be your 300 points. Well, basically our class was 3 chapters. Chapter 2 is our intro. We did that over the first few weeks. And so you're going to get topics like the limit of a function, techniques like factor and cancel, conjugate method, that type of thing. We're not going to ask you anything about the sigma delta stuff. We basically did that in 20 minutes, if I recollect. We did continuity, limits at infinity. The limit is x tends to infinity of x squared plus 1 over 2x squared plus 1, things like that. Derivatives is rate of change, velocity, acceleration, such like. By the time we get to here, I don't know why I've got my chapter numbers up, but by the time you get to here, that's where the shortcut starts. So you'll be able to do things like the power rule, which is differentiate polynomials, product rule, quotient rule, trig, chain rule, implicit, log, derivatives of inverse trig functions, some more velocity, acceleration. These questions 3, 9 are the ones like a sphere is expanding, and dr by dt is 50. What's dv by dt? It's also those questions where the boat's sailing north and the boat's sailing south, and they're 2 miles apart, and how far apart are they? The rate of change, those kind of questions. Do you remember the linear approximation ones? That's differentials, that's where they belong. How to find max and min values, the mean value theorem. How to find increasing, decreasing, local max and min. That's all first derivative stuff. And then concave up, concave down, and points of inflection. That's all in that group. L'Hopital. You won't be given questions where you're being asked to sketch the curve. They take forever in the day. And you certainly won't be doing 4-6 as a question because Desmos does it for you. Then you have optimization. Right. I'm definitely going to give you a question on that in section 2, and antiderivatives, you're definitely going to get a question on that. So that's the kind of the big picture. That's what your final is going to contain. Anybody want to start with a question or a topic or whatever?
Yeah, are we going to see? Are we going to see questions that we haven't seen yet? Because I've noticed on the exams, there are questions that we get asked that we haven't actually gone over in class or in the homework problems.
Depends the way you're saying that. Everything you've done, what you might not know is that, I'll take an example, an optimization question. We've done lots of them, but that doesn't mean we've done every possible one. Maybe the next optimization question you get will be about a ladder trying to crawl up a wall or some story. Or maybe it'll be trying to fill a tank up in the most efficient way. Or maybe it'll be about maximizing your profit in a business context. You won't have seen those particular questions because optimization questions, everyone is unique, but you will know the method, right? And so in that case, yes, you'll see questions that won't be exactly carbon copies of any question, but you will be able to do them because you will know the method, right? Can I think of other examples of that? You know you haven't differentiated every possible combination of functions in the world. But if I gave you e to the x to the power of x, you could still do it. It would be a product rule with a logarithmic differentiation after it. So I'm not saying I would do that question, but I mean, that's quite a hard one actually. But yeah, you'll get questions that might seem to you to have not been covered, but the method that you used to do them, you will have covered. Nice long answer for yes, you're going to get to see questions you think you haven't seen. Right, what's next? Any topic in here that you would like to go over an example of or whatever?
Yeah, I got another question.
Go for it. Yes.
So, let me regather my thoughts. Is it still going to be open notes for the final exam?
Excuse me. Yeah. The rules are pretty general, but let's make sure they're clear. If you've got it printed, if you've got it written down, if you've got it in a card, or if you've got it on your tablet, basically the same information, then you can use it. You can use, you know, tables with derivatives on them. You can use notes, all that good stuff. Totally okay with that. And you won't be able to use your WebAssign past questions because WebAssign will have disappeared and none of those questions will be visible. Right? And you won't be able to use practice finals or anything like that because they'll all have disappeared by then. The place where it gets where you're not allowed to do things are you're not allowed to communicate with a person. That's the short way of saying it. So you can't talk to someone for any reason to do with the final, and you're not allowed to communicate with software. I know it's not a person, but there is software. You were talking, Keith, there's one you can plug in stuff and get derivatives. So you're not allowed to do that. Or use Mathematica or lots of other software out there you could use. So that's not allowed. You're not allowed to go to tutoring sites and anything like that. That would be considered communicating. So that's not allowed. But if you've got it physically written down on paper, then you are good to go. You can use it. I would probably advise you to try and organize your notes. I mean, you could just say, well, I'll print out 400 pages of stuff. Well, yeah, but if you have to go looking through 400 pages for every question, you'll never get finished the final in time. Right, so you have to be organized about it. I would look at the things that are really useful and have them easy to me. Having a table that just has standard derivatives on it. Somebody says, what's the derivative of tan at secant squared? I'd have a unit circle handy. They're helpful when you do anything with trig. Right? So I'd have a few very useful things on their own, some easy to get to, and then whatever else after that is your choice. Next question. That was a good question. Want me to pick a topic?
Oh, I got a question for you.
Good. I'd rather have questions.
Yeah, I'm sure. Can you cover the steps? Well, I think I have the concept down, but I just want to review and make sure that I got it. But when we're asked and we're given the equation of a tangent line, we're given the curve of a tangent line, and we're asked to solve what that tangent line is from point P to point Q. Can you go through just the steps? I don't need a specific problem solved, but
Some
my
mention.
biggest,
Let me put some in just so I've got something to work with, right? So suppose I did a function, right?
yeah,
And are you saying there's a point P and a point Q? So let's say it looks like that. When like P is here and like Q is here. Is that the kind of question you're talking about?
yep,
And so we're being asked to find, what are you wanting to find? The slope between P and Q?
right,
Okay, so, and the steps would be, well, first thing you need to do, obviously, is find the coordinates of P and Q. Now, let's suppose that P was 1 comma, what would that be? Well, let's make it 2 so it's not a weird number. So P was 2 comma -1, right? Just for argument's sake. Then Q would be, well, if we were talking about trying to get a tangent line, Q might be 2.1 and you don't know its y coordinates. That's the most typical way. So first thing you do is get coordinates of P and Q. One of them you might already know. And the other one, we're going to find out. So to get the y coordinate, which is this guy here, you go up here and you plug in 2.1 and you'll get the derivative. So let's see what that would look like. So on my calculator, it would be 2.1 squared, add 2 times 2.1, take away 1, and I would get 7.61. So your first step would be to make sure that you find the coordinates of P and Q. The second step, to find the slope joining P and Q, and the notation that we would use would be something like that. M means slope PQ, slope of PQ, is to do f of B, take away f of A over B minus A. That's how you would do it. And you might say, well, who's all this A and B you're talking about? A is essentially that guy, and B is that guy. It's the x coordinate of the 2 points. So in this particular question, you would be finding the value of the function at 2, take away the value of the function at 2.1. Did I get that the right way? No, wrong way around. 2.1 and 2, 2.1, 2. And that would be 7.61, and that would be -1, and that would be 0.1, and you end up with 8.61 over 0.1, which I would get is a rather large answer of 86.1. So, recap, find the coordinates of the 2 points, use this formula to calculate the slope, plug in the numbers, get your answer. Now that type of question would be way up here around about 2.1. It's almost like the first thing you would see. Question like that is really not worth a section 2. You know, 25 points in section 2. So a question like that is more reasonable to expect as a multiple choice. So it's going to be worth about 5 points if you get one at all. Is that what you were thinking about, Charles?
yep. Thank you.
Okay. Okay, where are we off to next?
Yeah, I just sent everybody an email. I found a really good unit circle diagram with a table that has everything from 0 or 2 pi through 11 pi 6.
Gotcha.
It's got for sine, cosine, tangent, cosecant, secant, and cotangent, along with a copy of two of the reference cards from the back of the textbook that are going to be absolutely invaluable.
Okay, so that was a lot of help. Thanks, Keith. So when you say you're sending an email, I guess I don't know that you can do that. I know I can send you. So do you have the feature that you can send an email to everyone in the class, just like I have?
Yeah, it's through Canvas.
Okay, so people who are not here will also get that email, correct?
Absolutely.
Oh,
Yep.
great. Because if it wasn't, I would say just send me it and I'll do the rest. Right, that's helpful.
Can you work implicit differentiation and logarithmic differentiation and kind of explain the difference between the two? They just are looking the same to me.
Okay, so implicit versus logarithmic. Well, an implicit one would be one that would look like this kind of thing. It would be an expression where X and Y's are jumbled up. That is what an implicit would look like. And you're going to find the derivative. Now, if you want to know what kind of look does logarithmic have, well, it has the most useful one is that it is used for differentiating really weird powers. So you use logarithmic on that. And you can also use it to do really weird and ugly powers and square root questions. So if I wanted to differentiate this guy or a weird power like this, that would be a logarithmic question. If I wanted to differentiate, x cubed y squared plus y cubed plus x e to the y, things with x's and y's all jumbled up, typically equal to a number, then that would be an implicit differentiation situation. So you're a little bit more clear about when each would happen. They're quite distinctly different, right? Have you noticed that these have x's and y's all over the place, and these don't, right? These have a y equals, and these don't, right? So they're quite specific. What makes this logarithmic? Weird power. What makes this logarithmic? Really ugly calculation. Theoretically, I could do this question using a combination of product, quotient, and chain rules. I mean, theoretically. God, it would be ugly, and it would take me forever and a day. And then when I came to do the style points at the end, I would probably just throw my hands in there and walk away from it. It would be so massively ugly that it wouldn't be really practical. But theoretically, it would be doable. On the other hand, if you do it logarithmic, it's much cleaner, much nicer. Do you want me to do these two, or is that enough for you?
Could you go ahead and do both of them?
Sure.
Thank you.
You got to remember when you ask questions, you're not just asking for yourself. I guarantee you a lot of people saying, oh, I'm glad she asked that question because I had trouble with these guys as well. So let's start with the implicit one. In implicit differentiation, you basically take the expression and you differentiate it. But there are certain rules that you have to apply that only really exist in these questions. And that is, you've got to realize that the x's and the y's both are functions of x. Now, what does that mean? Well, if I want to differentiate this guy, I have to call it a product rule. Now, you differentiate this guy, you get 2x. You leave that guy alone, you get y. You leave this guy alone, you get x squared. And then you get to this, which again happens only in implicit. You differentiate y with respect to x. Technically, you'll get 1, but you always get that dy by dx bit. That's the bit that makes it all work. Right, so if you differentiate y, you get 1, right? That guy. Now, we move on to this one. And this also happens to be a product rule. So it's going to be f dash j plus f of g dashed. Now, if you differentiate this guy, you've got 1. Leave the other guy alone. Leave the first guy alone. And now I'm going to differentiate the sine of y. Well, if you differentiate the sine of y, you get the cosine of y followed by that dy by dx. So whenever you do implicit differentiation, if the thing you're differentiating has a y in it, right? Like it's y cubed, sine of y. Differentiate it using the usual rules, power rule, sine becomes cosine, whatever it is. But remember to finish with dy by dx. And then you differentiate the number and you get 0. And so that would essentially be the first step in the differentiation by implicit. You would differentiate all the guys using the rules that we talked about. And then the next step is pretty much standard. Some of these terms have dy by dx's in them. In particular, that guy has one. And then, so does this guy have one? So what you're doing eventually is you're going to solve for dy by dx. But to get to that point, we have to use my, as long as you do it to both sides, it's okay rule. So I'm going to leave these two guys exactly where they are. I'm going to subtract a 2xy from both sides, and I subtract 1 sine of y from both sides. And that's pretty standard. You're going to do that pretty much all the time. Can anybody remember what the next step is, which is also pretty much standard? What
I think
happens here?
you're gonna factor out dy dx.
And when you do that, you then have,
And then divide both sides by x squared plus x times cosine y.
and that again is also pretty standard. So when you do implicit differentiation, a lot of the steps end up being the same kind of step each time, even although the the details are different because each function is a little bit different from the next one. Differentiation, sometimes you need to use a product rule, sometimes you don't. Get the answer. Get all dy by dx's on one side, anything that's not on the other, right? So you add and subtract to both sides to make that happen. Pull out dy by dx as a common factor, and then divide by this horrible mess, and there is your answer. So when you do implicit differentiation, your answer will also be a combination of x's and y's. Now, if you wanted to look at, let's say, oops, try that again. Let's suppose you wanted to do logarithmic differentiation. Right. This one is more standard than that one, right? Because that one, there's lots of variations on it. This is pretty much, what do you do with weird powers? What do you do with, sine x to the power of cosine x, right? X to the power of log x, right? Weird things like that. Implicit differentiation is the way to go. So the first thing you're going to do here is take the natural log of both sides. So natural log of this guy equals the natural log of that guy. Pretty much guaranteed. You also have a little bit of algebra to do, simplifying. The log of a power can be written down as the power times the log. Are you happy with that becoming that? It's the third law of logs. Like log of a cubed is 3 log a. It's that kind of rule, except that's the power, right? So power outside, log. And that's pretty much step 2. And then step 3, you differentiate. And this is a bit that might make you think, and you're right in a way, Tessa, but it reminds me a lot of implicit. And this is the line that looks like that. Because when you differentiate log y, you do get 1 over y times dy by dx. Isn't that exactly what you would do in an implicit world? So that's where the overlap happens. Now, on the other hand, this thing here is just a product. So I want to differentiate this guy. I have to use a product rule. And that's very common in these questions that you end up doing a product rule here. So I have got some details. Differentiate a sine, you get a cosine. Leave the other guy alone. Plus, leave the first guy alone. And differentiate that guy, and you get 1 over x. Okay, what do we do next? Well, if you multiply both sides by y, you'll have isolated the dy by dx, which is what you're trying to do. And that looks very nice, but it's not actually the final answer. In logarithmic differentiation, the answer should all have x's in it. In implicit, it's okay to have x's and y's in your answer, right? The derivative will pretty much guarantee you have that. So what is the last line? Well, the last line in this process will be cosine x times log x plus sine x over x. But instead of y, replace it by what y is equal to. So there's your final answer in terms of x's. So when you did implicit, your final answer to what the derivative is equal to, which I now can't seem to find, yeah, is a big combination of ugly x's and y's. That's pretty much what you're going to get when you do logarithmic differentiation. If you do it all the way to the end, your answer will have nothing but x's in it. So there's a little bit of difference in the way the answers look as well. And a little bit overlap maybe here.
Thank you, that helps.
Do you want me to do this one or should we skip this one? I don't mind either way. Anybody got a preference?
I wouldn't mind seeing that one.
Okay.
I know I'm getting kind of tangled up in multiple rules, so I wouldn't mind seeing it.
So we do not want to do this question by using a combination of product rule, quotient rule with lots of chain rules, right? You don't want to do it that way. That's why we're going to do it using logarithmic. If you think the method you're going to use, try and predict how hard it's going to be. So if you say to yourself, oh yeah, product rule, I'm going to have to do a quotient rule. Wait a minute, these things are also going to have chain rules in them. Oh, I don't like the looks of that. If you say, I don't like the looks of that, you're probably doing it the wrong way. There must be a better way to do it. Because, you know, I'm not going to give you a question. That question easily could take me 20 minutes if I did it the long way. Easily. Maybe even more. I haven't even looked at what I would have got, but I'm sure it'd be a really ugly style point when I'm finished. I mean, just look at it. There's bound to have some really ugly bits to it. So we're not going there. If you are going to use logarithmic differentiation, I'll remind you of some rules. And these rules work in both directions. So the log of two things multiplied can be rewritten as a log of the first thing plus the log of the second. The log of two things being divided can be rewritten as a log of the top thing, take away the log of the bottom thing. And the log of e to the power of n can be written as n times the log of a. We call these the laws of logs, right? That's their name. And I'm going to use these guys right now. First thing I'm going to do is take the natural log of both sides. And while I'm at it, I'm going to take that square root and call it a half power. Okay, so that was just step one. The normal steps that you do in logs, right? We did it with the last one. Take the log of both sides. Now, how this one simplifies or breaks apart is going to be a little bit different and a little bit more involved in how this one works, right? This one was basically rule 3, right? A power becomes the two things multiplied. This is like a to the n log a, right? That's what this one is. This one here has got a lot more to be done to it. I'm going to take this guy times this guy divided by that guy. And that splits into the log of the first guy plus the log of the second guy. Since you're dividing, take away the log of the third guy. Now, you see it's a times b divided by c. Log of a plus log of b, take away the log of c. Does that make sense? Multiply, you add the logs. In the bottom is a divide. Divide means subtract that log. Now that's nice, better, but if I then use rule 3, this one, I can turn these into something that's a little bit easier to differentiate. This, oh, it's got an extra 0 from someone. This guy now becomes 100 times the log of x plus 1. This guy becomes 3 times the natural log of 2x minus 1. And this one becomes 1/2 the natural log of 4x plus 1. So each one of these guys I've used rule number 3, right? This guy 100 becomes 100 log that. Log of this guy cubed is 3 times that. A half gets you a half times that, right? That's the third law. Now at this point, we've got it to the nicest it can be, right? You can't really do much else right now. So we then move on to step 2. So it took a little bit longer because there are a lot of bits in step 1. And we find the derivative. So the derivative of log y is 1 over y times dy by dx, right? Just like it was here, right? Now, in this case, I have 3 different things to differentiate. And I forgot that I had a square in it. Right. Yeah, fix it. Each one just differentiate on its own. If you differentiate a log, you get 1 over the thing. So 100 logs get you 100 over x plus 1. So the derivative of that is that. Right, you move to this one. Differentiate this guy. You're going to get that. I know you're going to get a 3 on the top, but won't you also get, it's a chain rule. So it's not just 3 over 2x minus 1. Isn't it going to be 3 over 2x minus 1 times the derivative of the inside function, which is times 2, and that's why that's a 6 and not a 3. And then you take this one in, right? If you differentiate this guy, you're going to get 1 over 4x squared plus 1. And that half is still there, but aren't you also going to go times 2x? Maybe there's too much going on here. There. That's what it would look like, right? 1/2 over this times the derivative of the inside function. So I now have that ugly fraction, this ugly fraction. That tidies up a little bit.
On the last one, did you
This one.
already, yes, did you already simplify? Would the chain rule not be,
I did it. You're right. It should be 8x, shouldn't it?
Okay,
I did it in my head, but I shouldn't have. Yeah. So what
I
we got?
totally did it.
Yeah. So we're looking good. The last two steps are pretty much guaranteed. When you get to this stage, the next two steps are multiply both sides by y. And then the one after that is just replace the y by its original. And a lot of people go from this line to that line directly. They kind of combine the two. Now, when you look at how ugly that answer is, and it truly is ugly, but it only involved 1, 2, 3, 4, 5, 6, 7 steps, and you could have said 6 if you skipped this line. If you try to do it product rule, quotient rule, combination with chain rules, and then after that, try and factor out, wow, look at that as a common factor. You're going to have a lot of work. So I hope I've convinced you.
Can you move your paper up just a little bit?
Sure.
Thank you.
So have you convinced you that this little niche market called logarithmic differentiation does a good job for weird powers and really ugly expressions with powers involved as well?
Yes,
That's, kinda, that's its job.
Yeah. Thank you.
You're welcome. Okay, Keith, what's the difference between a loaf of bread and an elephant?
No idea.
Oh, well, then I've never sent you to the shops for a loaf of bread.
That's awful.
He fell for it. That was awful. Come on, Tess, was that awful?
Yes.
Yes. Okay.
Yeah. So the one that I had probably the most trouble with out of all the sections was Lavadals. I cannot English this morning. I haven't coffeed yet.
Okay.
Yeah. This one on the exam, I don't know what I was doing wrong. I don't even know what I was doing. So
right. So do you have the question handy? I could just go over it.
No, it's on the exam, so I don't have it pulled up.
Right.
I have a couple that I saved of them.
Okay, you want to chuck one in, Coral, and I'll write it down?
Sure. The limit of theta as it approaches pi over 2. And then the function is 1 minus sine theta over 1 plus cosine of theta.
Right. Okay, so I want to just check that it's indeterminate form, because you can always get caught out by that. So 1 take away the sine of pi upon 2 over 1 plus the cosine of pi upon 2. Right, so if you find the sine of pi upon 2, it's 1, so that works. You've got 0 on the top. And the cosine of pi upon 2 is 0. Oh, so the answer's 0. You don't need to use L'Hopital. If that's the question.
I think that's where I've been getting caught up, is like when to use it and when not to use it.
Oh, wait. First question. The answer to the first question: when do I use it? You only use L'Hopital when you plug in pi upon 2 you get 0 over 0 or infinity over infinity, right? That's the two situations where L'Hopital does its thing. And
What if you get 0
Mhm.
over a number?
if you get 0 over, you said something, I didn't catch it.
0 over a number, like 0 over 3.
Oh, then the answer is 0.
Okay.
And if you get 0 over infinity, the answer is 0. Right? And if you get infinity over z, the answer is infinity, right? So there's only certain combinations, that's these two that actually generate a problem. So you need another one that actually works.
I saved a second one.
Go for it. What's that one?
The limit of x as it approaches infinity.
Okay.
The natural log of 3x over the square root of 3x.
That's one ugly looking guy, isn't it? Now, if you plug infinity in, the log of infinity is infinity. If you plug infinity in here, the square root of infinity is infinity. So that one is going to be indeterminate form, so L'Hopital can be used. Now, what L'Hopital says is that the limit as x tends, in this case, infinity, of f of x divided by g of x, you can get the answer to that limit by finding the limit as x tends to infinity of the derivative of the top divided by the derivative of the bottom. Right, that's L'Hopital. That's his rule. So in this question here, I should be able to take the limit as x tends to infinity of the log of 3x over the square root of 3x, and I should be able to use L'Hopital on it. And I'm going to have to do a little bit of extra work before I use L'Hopital. It's not a lot, but don't you have to call things half powers? Now, was this the square root of all 3x, or was it the square root of 3x? Because they're not the same thing.
It was the square root of all 3x.
Right, so that's a little bit weird. So what I just did there is correct. You agree it's 3x all to the power of half. Right. So, L'Hopital's rule. You are still going to find the limit as x tends to infinity. If you differentiate the natural log of 3x, you'll get 1 over 3x times the derivative of the inside function, which is 3. So that gives me, cancel, that gives me 1 over x. Okay, if you differentiate 3x to the power of half, right? 3x all raised to the power of half, that's also a chain rule. It's 1/2 3x to the negative 1/2 times the derivative of 3x, which is 3. So I have 3 upon 2, 3x to the negative 1/2 power. And that is really weird looking, but it is going to come out okay. What I need to do in this question now is not try and plug infinity in, because if I try plug infinity in, I won't be able to get an answer, right? It'll be indeterminate again. And normally if that happens, you would just keep doing it until you got an answer. But you should also say, is there a better way to write that might eventually allow me to plug infinity in and get a result? So that's what I'm going to do right now. I'm going to see if I can algebraically make that guy easier to deal with, right? So it's 1 over x times over 3/2, and I'm going to do times this guy to the power of positive half. Are you comfortable but a negative half on the bottom becomes a plus half on the top?
Yes.
Right? You know that 3/2, I know it's a waste of time, this thing, you know that guy there? He's on the bottom. Can't I just turn that into 2/3 then? Are you comfortable with that line? Try to take it slow.
Yeah.
Right? a fraction on the bottom becomes a multiplication of its reciprocal. Now, again, taking as much time as I can, I'm going to do that. Three x to the half can be separated as 3 to the half times x to the half. Now, that x to the half will cancel out part of that guy, and you're going to end up with an x to the half on the bottom. Are you comfortable with the x on the top and the bottom cancelling out? Half away from that leaves me 1/2 there. And now we have that guy. And now that I've done that, how about that guy, right? Okay, so I want to find the limit as x tends to infinity of this ugly fraction, which with a lot of algebra, I figured out that it can be rewritten as 2√3/3 times 1/√x. And now I'll put infinity in. Brute force. Well, 1 over the square root of infinity. Would you agree that's 1 over infinity, which means it's 0? And 0 times any number is 0. So my answer is 0. And the trick was to realize that this answer here could, if you manipulate it enough, turn into something that is easy to evaluate when x is infinite, right? This here is basically going to be 0. Now that's a little bit unusual as a L'Hopital, but it is a L'Hopital question nonetheless. A more typical question, just to show a more straightforward one, might be something like x cubed is 4x over that guy. That's a pretty standard L'Hopital question. If you plug in 2, you get 0/0 in determinant form. So I can do a L'Hopital on it. And when I differentiate the top, I get 3x squared take away 4. When I differentiate the bottom, I get 1. And in this case, I can plug in 2. And I get 12 take away 4. I get 8. That's a much cleaner version. That one's yucky, but this one's quite nice.
Yeah, I just got caught up on that last one just because when it became to the point to write it a different way, I was like, I don't really know how to do this. I was like, do I just keep
it was the
trying?
algebra. Yeah,
Yeah.
it was the algebra. Yeah. I think we've all noticed that Calc 1 is an algebra class more than a calc class, right? And that's just what it is. You know, we have various rules of algebra that we might be a little bit rusty on, especially when you start looking at expressions that look like I've never seen that before. Well, I guess you haven't seen that specific one, but the process that you use is pretty much the same. Yeah. Write it down as powers of x as best you can, and hopefully some simplifies.
Professor, I have
Yes.
another question about L'Hopital.
Go for it.
So it was the take the limit as x goes to 0 of e to the x minus 1 over x to the 7th. But the minus 1 was not in the exponent.
Oh, I got you. Right. Oh, I like this question. You might not like it, but I do like this question. Can we just, can I just say, look, it's definitely indeterminate form, right? You're going to get 0 over 0. In fact, you're going to get 0 over 0 a lot of times before you finally get the answer. Now, if you differentiate the top, then you basically just get e to the x. And if you differentiate the bottom, you get 7x to the 6. And, oh, I take it back. Unless there's more to this question than I think, you're going to get e to the 0 over 7 times 0 to 6. You're basically going to get 1 over 0, so your answer's infinite. I thought that you were going to get, you know, you'd have to differentiate it like 7 times to eventually make that disappear, right? A 7, a 6, a 5, 4, 3, 2, 1. But no, you don't need to. Oh,
Okay.
you got
got-
to every time you differentiate, you should always plug in the number to see if there's an answer. Now, why is that important? Well, if you just keep going, which is what I was thinking of doing, L'Hopital will let you keep going as long as you want, right? As long as you can differentiate it, you can keep going, but you shouldn't just do it because you can. So let's put in a number like, you know, start again. Kind of show you what I'm getting at. Let's suppose I wanted to do that. Now, I don't need L'Hopital to do that. Isn't 3 squared 9 and 3 plus 1 is 4? So the right answer is 9/4, right? Couldn't we just plug in 3 and get the answer? One of the weird things about L'Hopital is that if you use it when you shouldn't, you'll get an answer. It just won't be right. So let me do this, fella. If I do L'Hopital, on the top, I get 2x. On the bottom, I get 1. And if I plug in 3, can you see that the answer I get is 6? It's not the correct answer, which is 9/4. So the moral of the story is when you plug in the number, do you get 0 over 0, right? So if I plug it on up here, oh, well, if I plug it up here, I should have noticed that right away. I don't need L'Hopital for that. 1 over e over 0 is just infinity. Actually, I could have got the answer there. So I was just kind of lucky that L'Hopital gave me the right answer in the first place. Bit surprised that was x to the 7, but yeah, it is what it is.
So I've
Okay,
got,
thank you.
Yes.
so I've got one. It was number 25 on exam 6.
Okay.
Evaluate the limit. Limit of x as it approaches negative infinity. X squared times e raised to the 6 times x power.
Is that it?
It is.
Right. Now, to be able to do this question, we have to write it as a fraction. Because L'Hopital doesn't work when 2 things are multiplied. It can only work when you have an f and a g. So the first extra line that you didn't need in these ones, because they are fractions, is that you make it a fraction. So I decided to go this way, right? E to the 6 is that one. Are you comfortable that algebraically these are equivalent?
Yeah.
Now, if you plug negative infinity into the top, you get infinity squared, you get infinity. And e to the plus infinity, because negative 6 times negative infinity gets you plugged infinity, is also an infinity. So I have basically got infinity on the top, infinity on the bottom. So it means I can do L'Hopital. So it's going to be the limit as x tends to negative infinity. If you differentiate the top, you get 2x. If you differentiate the bottom, you get e to the negative 6x times negative 6. If you plug negative infinity in here, you get some version of infinity on the top divided by another version of infinity in the bottom. So again, we know that that's indeterminate form. So I'll do L'Hopital one more time. If you differentiate the top, you get that. If you differentiate this guy, you'll get e to the negative 6x times another negative 6, so you end up with positive 36. If I now put in x for negative infinity, I get 2 over 36 times e. Negative 6x is negative 6 negative infinity, so that's positive 6 infinity, so it's positive infinity. You comfortable with negative 6 times that guy is plus infinity?
Yes.
And we know that plus infinity, right, or e to the plus infinity, is also infinite. And we know that 36 infinites are still infinite. And we know that 2 over infinity is 0, so the limit would be 0.
So then any number over infinity is always 0, and 1
Yes.
over 0 is always infinity.
Yes. As long as they're positive, yes.
Yeah, I can see where I had a problem.
But is a problem going away now?
Well, I wouldn't say all my problems have gone away, but that one has.
That one has. That's all I can hope for. L'Hopital are good. I like L'Hopital questions. They are not saying they are going to be in the test, because half the things you study for won't be. In fact, if you look at my list and we think of each one of these as being a potential question, in section 2, for instance, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. There are 23 potential questions and only 10 questions. Because you see, like, half the things you're going to study for might not appear. But, thankfully, we have got multiple choice. So I guess if you throw in multiple choice, there's going to be a lot fewer things missed somewhere, right? Multiple choice are going to really be for questions that shouldn't take you more than 3 minutes to do. So if you think, oh, I'm going to do this, and then I'll have to, I'm going to do a product rule, and then I'm going to do a chain rule, and then I'm going to do a lot of algebra, and then I'm going to plug in 42. That's probably not the right way to do that question, right? So when you're thinking of multiple choice, it should be pretty much, 3 minutes or less, and that's a good guide. If you start a question and it just gets ugly and starts growing into a monster, the correct answer, Madison, is C, or A, or D. Since Keith is ex-military, isn't the answer in the military C?
Oh, that's just the answer to everything except life, everything, and the universe. So that
Well, that's
would be
42.
42.
Yeah.
So, and
So-
don't panic.
And don't panic, correct? You know the series, well done. Yeah. So make sure that a multiple choice should not take you 20 minutes. If it's taking you 20 minutes, you've just wasted 20 minutes, right? You might as well just throw the coin in there and pick it. So, student, very bad student, not like you lot. Never turned up for class, never did homework, never did anything. Turns up on the day of the final exam. And he comes in late. And he walks by the professor, and there's only one seat left vacant right in front of the professor, and he sits down and he gets handed the exam, and he looks at the exam, and it's his lucky day. It's 10 multiple choice questions, but it's either A or B. That's all it was, right? True or false, A or B. And a big smile goes on his face. The professor's watching him as he reads each question, and as he reads each question, he throws a coin in there and he goes, next question. All 10 questions. Professor's watching and thinks, well, I know what he's been doing, right? And so he expects to get the paper back, but he doesn't. The student turns it back to the front again, looks at the first question, throws a coin in there and goes, throws the coin in there for the next question, goes, and he goes in and says, what are you doing? Oh, he says, oh, I'm checking my answers.
Uh,
No, Okay, try this one then. This student always turns up for his exams, his finals and things like that, with his Seahawks gear on. Right, his baseball cap, his t-shirt, the lot, right, everything. Seahawks pen, everything. Every exam, every final, whatever, he turns up with this Seahawks stuff on. Finally, his friend says, "Why do you do that? Why do you always wear your Seahawks stuff for your exams?" And he turns around and he says, "Well, I know I'm always going to pass even when I shouldn't."
Wow, still too soon.
Still too soon,
Still
Keith?
too soon. It
Still
will
too
always
soon.
be still too soon.
Okay, sorry.
Just like when people want to talk about, the Super Bowl with the against the Steelers. Yeah, still it will always
Still
be
too
still too soon. Even when I'm like 85, it's still going to be too soon.
So in a couple of years from now then, Keith.
Well, about a year.
Okay.
I just look good for my age.
Oh God, I've lost my place here.
Speaking of preseason game tomorrow night, I'm going to be there.
You will fit. I am a Seahawks fan, so I will be there as well. Well, not physically there, but I will be hopefully watching. So I'm losing my place here, so let me go back into what the heck I was going to do. That's this guy here, right? A couple of strategies on how to take exams. Some people have no problems with exams; they don't really get stressed out. Other people, it's a big deal, so I can understand your situation. So here are my opinion, from my experience, some of the strategies you should do. When you're doing section 1, do the questions. If they take longer than 3 minutes, pick C or whatever letter of the alphabet you like. Put a little asterisk beside it. You can always go back at the end if you've got time and, maybe change your mind. In section 2, spend a little bit of time just scanning over each question. And do them in the order, not numerically 1, 2, 3 up to 10, but do them the order of the ones you know how to do. So if you look at a question and it's a L'Hopital question, and you think, yeah, I've spent so much time in that, I could do those in my sleep, that should probably be your first question. And maybe your last question should be implicit differentiation. I never get those ones right. I always screw up somewhere. I'm not even sure how to start some of them, right? Make that your last question. So do your questions in the order for you, and it'll be different for each person, of what I can do to what I can. And the main reason for doing that is it's a good time management thing. If you do all the good stuff, you'll have hopefully enough time. You can then spend as much time as you like on the last 2 questions. Maybe some will come to you. Psychologically, it's good. The worst thing you can do if you do them in order is hit question 3. And it's something you're not really good at or really sure about, and you spend 20 minutes doing it, and then it's rubbish, and you go, ugh, and you try it again, and then you do another 10 minutes. You see, you could use half an hour on a question, and it's just not psychologically good for you. Because when you run out of time or start chasing your tail now because you've got a clock tick-tock thing going. So that would be my advice. Multiple choice first. If you don't know how to do it in 3 minutes, the answer's C and move on. That way you can zoom through them pretty quickly. Technically half an hour, right? 3 minutes each. Probably take a little bit longer. And then the other 2+ hours, section 2, do them in the right order. Second piece of advice, when you are doing section 2, try and show me as much work as you can. If you make a mistake, but I can see exactly where it happened, then I will give you partial credit. but it's much easier for me if I see 6 lines of working and I can tell exactly where it went wrong than if I go A to the middle to the end. Because if you do it that way, it's very hard for me to know what you did wrong, unless it's something obvious like, oh, that should be a minus. That I could probably detect. Also, if you go A, B to the answer, I'm going to assume that you've just used some software and you've been cheating, because the software doesn't typically tell you everything that you need to do. And I know that you couldn't possibly get from step 2 to step 3 in one go, right? There's too many style points, there's too many things you needed to do to get to that. So that is not good. And that will probably get you a big fat 0. And I will not think nicely of you that you've cheated. So don't show every bit of working you can. Now, some questions, it's really not that possible. Would you agree if I said differentiate x cubed plus 2x plus 7? There is no working because it's an answer, right? There's not a lot you could do to that. So don't get too caught up on, situations where it's pretty clear there is no working, right? But that same situation, if I went and asked you to find the equation of a tangent line at the point 1, 5 of a cubic, would you agree that's not a one-line deal? You can't just say 3x plus 2 and think, yeah, oh, he did it all in his head, or she did it all in his head. So show you're working. It's a good way. If it's half right, you're going to get 50% of the points. If you get a question where you need to know A before you can do B and C, but you don't know the answer to A, write down a rubbish function for A and then use it to get example. Suppose I went and asked you to find the equation of the tangent line to a function at 1, 2. And the function I gave you was x to the power of x, and you went, I don't know how to do this. Then you might just say that's the end of it. But couldn't you just write down the derivative was x to the power of x times sine x? Yeah, whatever. Couldn't you then find the equation of the tangent line using your derivative, even although you know it's the wrong function? Because what you've done there is you've shown me that you know how to take a derivative, use it to get the slope of the tangent line, then use that to get the equation of the tangent line. So you get half of the question, right? So you'd get half the points. So when would that? Can you imagine doing an optimization question? You know, the ones about boxes with no lids, or farmer cutting his field into 7 bits and you just can't figure out how to get the function just have x's in it. Well, make up a function that has an x in it that is kind of like the guy that you had, maybe turn the y into x squared or something, right? And then do the rest of the question based on that. Again, you've only got half of it right, but isn't 50% of the points better than none? So if it's possible, and there's an ABC going on, make up the missing piece of the puzzle so you can continue the question. Anything else?
Did we do an average velocity question from 2.1?
Okay, average velocity. Turn that in space. Okay, so suppose you have a position function t cubed plus 2t, and it starts at the 1 second mark and it finishes at the 5 second mark. And I would like to get the average velocity from 1 to 5. So the average velocity is, call that A, call that B, can be found by just basically doing this guy. Do you recognize that as the same rise over run that you would use? Because the average velocity is actually the slope joining this curve right? When t is 1 to here, when it's 5. So the value of this function at 5, take away the value of this function at 1, divided by 5, take away 1. Right, that's 125, that's 135. Take away 3 over 4, which is 132 over 4, which is 33. Okay, so the average velocity, let's say the units were meters per second, would be that. Now, I've seen questions where you get a 1 to 5, but you get like a 1 to 1.1, and then you get a 1 to 1.001. Do you ever seen those ones where like a batch of 4 or 5 of them? And
Yeah.
yeah. Now, what is happening here is that the distance between the start number 1 and the finish number B gets closer and closer to closer. So imagine that this answer was 33, right? And then this answer, the average ended up being 30.7. And this one, the average ended up being 30.003. Couldn't they then ask you, what would be your estimate of the instantaneous velocity, right? And in this case here, would you agree that it looks like the answer is probably going to level off at 30?
Mhm.
Now, if you wanted to find the instantaneous velocity at the 1 second mark, then you would do the limit as, let's say, h tends to 0 of f of a plus h, take away f of a all over h. Or you could do it as the limit as a tends to 1 of, oh God, I'm gonna try to get my, there we go. X tends to 1 of that guy. Yeah, so you could use either one of our two formulas, and that would just be a whole lot of, you know, the f dash a thing. That's very similar to that. And if you did it, I'm pretty sure the answer would come out to be 30.
I guess I kind of got caught up on this question because it was giving the original equation in sine and cosine.
Also, was there sines and cosines in it?
Yeah. And then it gave you the average velocity time periods, and it was getting as close as 1 as possible.
So it was like 1 to 1.1 and then
Yeah.
1 to 1.01 and that kind of thing.
Yeah, and the inside of the sine and cosine was pi t.
Okay. Like that guy?
Yeah.
Right. So for instance, if I wanted to do this average, right, it would be the value of the function at b, take away the value of the function at a, all over b minus a. So it's the same formula as I'd give. So it's going to be the value of the function, let's b, let's say, at 1.001, take away the value of the function at 1, all over 1.001, take away 1. Now that's a pretty messy formula if you wanted to calculate it. So let's just show you what that is equal to. It would be the sine of 1.001 pi plus the cosine of 1.001 pi. And that's why we have calculators, thankfully. I'll just make sure I'm in radians, which I am. Actually, when you're doing your questions in calculus, make sure your calculator is in radians. There's no need to ever worry about degrees typically. So let's get out of there. And you just simply just type it in. So 1.01 pi, add the cosine of 1.01 pi, and What did I get? I get negative 1.030917 watt change divided by 0.001, which means that this answer is negative 1.030,917. Now, that might worry you, but it's not actually a problem. I mean, it's just a big number. But surprised that it's that big number. I would have thought it would have been a nicer number. But evidently it's not. Which must mean that won't the limit probably be negative infinity?
Is when you're typing into the calculator, is that cosine 1.001 or is it just 1 pi?
Oh, that is just the first guy. You're right. I should have taken that into account. That's only this bit. I also need to know who he is. And it's a bit easier to do because he's the sine of pi plus the cosine of pi. Okay, so it's going to be a little bit nicer. What do you get? Well, you get negative 1.0309. Take away that guy. What is that guy? Cosine of pi. Oh, negative 1. So basically, you take away negative 1, which means you add 1. Okay. So what do I get? 0.0309 divided by that guy. So it looks like the answer's 30. You might want to check my calculations there because it's a right mess now. So see if I can do that cleanly. That's the original function. I'm going to get the average in the range 1 to 1.001. So I make that A, I'll make that B. The average will be the value of the function at B. Take away the value of the function at 1. All over value of B. Take away the value of A. That guy in the bottom is 0, 0, 1. This guy in the top, I'm just going to do it again. It's going to be the sine of 1.001 pi. Add the cosine of 1.001.
Is it the cosine of? Okay, I see.
Right. So t is 1.001.
Mm-hmm.
Right, for this guy. And then that's this answer here. I guess I'll write that down, which is negative 1.00314 roughly. Take away, evaluate it at 1. So it's going to be the sine of 1 pi. Add cosine of 1 pi. And the answer is negative 1, so we have that. This ends up being 0.00314 over 0.001. And I'll do that on my calculator as well. 0.00314 divided by 0.001. And the answer is 3.14. So if you want to find the average velocity in this range using that function, the answer is 3.14. I have got a gut feeling if you wanted to find the instantaneous velocity, I think the answer is going to be pi. Doesn't 3.14 remind you of pi, 3.1412? If I did a bit more accuracy here, that might have been even more obvious. So that would be my prediction. Actually, I don't need to predict that. If I wanted to, I could find out what the right answer is by using calculus. Because this stuff happened before we knew how to differentiate. So won't the velocity be the first derivative? And if you differentiate the sine of pi t, you get the cosine of pi t times the derivative of the inside function, which is pi. Plus, if you differentiate a cosine, you get a negative sine pi t times the derivative of the inside guy. And that would be the general answer. We are interested in the answer at 1. So that's pi times the cosine of 1 pi. Take away pi times the sine of 1 pi. And did I get a sign wrong? I did. Which is a good way of checking, because that's negative pi. Take away nothing, and that's negative pi. So actually, did you see by doing calculus, I fixed a mistake that I made?
Yeah.
And if you look, it's very easy, isn't it? To just look at that and put in a plus when that's bigger than this. So actually, you get that.
So when we're doing these earlier sections of questions, can we use like the power rule and the quotient rule and things like that to find the derivative?
No, you're not allowed to, because this question
Okay.
was asking for that. What you can use it for is to check.
Mm,
Say, I know what the answer is probably going to be, right? Because this told me. And so I should be able to look at this and look at that and say, yeah, can you imagine you did the math for a different question and the derivative, you know, the velocity, which would be the derivative at 2, was 7, right? Just for argument's sake. And you did the average velocity from 2 to 2.01, right? And you got the answer minus 6.98. Wouldn't that be an indication that you got your sign on? And you may want to figure out why it's negative when it clearly should be positive. If I did an average function and I thought the answer was 703.2, wouldn't that probably be an indication that I got something wrong with my divisions? Right? It's far too big. On the other hand, if I get an average and it's 6.891, wouldn't that be a reasonable answer? Because we know the right exact value should be 7. So shouldn't an average be pretty close to it? So I'm
Okay.
using the derivative only to check that the answer I got, you know, this way, which is the way you have to do it because it's an average, and matches it.
So how we know the difference between these average slopes and like the ones in the sections afterwards is that
Right, in the sections afterwards, we don't typically get you to do averages anymore. So
It's
once you
slope.
once you hit here, you really shouldn't be looking at finding the average of anything. Shouldn't you just be using calculus and getting exact values for things?
Mhm.
Now, in the test, I do them in chronological order. So if the question was question 7, is down here, you shouldn't be doing this at all. If
Okay.
it was question 2, yes, you probably should be doing this. Secondly, in question 2, they'd be asking for average velocity and then maybe estimate the instantaneous. If it was question 8, they would go straight into what is the velocity right off the bat. You wouldn't have to
More
do anything
specific.
else. Yes. So the questions, although they might look similar to you, one of them asks for averages and then it says find the instantaneous. The other just says tell me the velocity right off the bat.
Okay. That helps me better because I feel like they got kind of muddled together a little bit.
Yeah. Weber saying isn't always your friend when they do things. For instance, it sounds like some of the L'Hopital questions didn't need L'Hopital. Can't you just plug them in? I'm 99% sure, didn't I say to you something along the lines of when you're doing L'Hopital, you should check for, you know, indeterminate form. Because if you do 10 questions and you check 9 of them, if you don't check the 10th one, isn't that the one you should have checked because you don't need to do L'Hopital? That's just the Murphy's Law of the world. And it seemed today anyway that the ones that were causing you trouble were actually the questions you didn't need L'Hopital for at all. If you just plugged in the number, it was 0 or infinity.
What I'm hearing is my problem is overthinking.
Ah. Now, in the big scheme of things, overthinking is better than underthinking. But somewhere in the middle is a sweet point that is a place that you'll get to. Okay, we're going to have to call it quits today.